So, in this lecture we will see the application of control system to a practical application, which is a vibration control of a beam. So, before actually explaining the control process, let me actually introduce the concept of vibration of a system. So, now the question is, what is vibration? So, vibration represents a motion of a system caused by the combined action of the inertial force due to the mass of the structure, elastic force due to stiffness of the structure. In dynamic phenomenon, wherein the system movement is a function of both time and hence the system is also a function of time. So, basically if you look at this tuning fork, when you give an initial disturbance, it vibrates, and this vibration is causing because of the mass of the structure and also the stiffness of the structure. So, how do we model the dynamic systems? So, the dynamic systems are modeled. There are in a typical regular system, there are translational elements, there are rotational elements. The translational elements are modeled using what we call the spring. The mass element is represented by a block m, and there is also going to be damping, because when you give an initial disturbance, after some time it dies out. What is the force that causes this dying out of the response? That is the damping force. So, normally there are various types of dampers. What we use is the viscous damper, is represented as shown here. There are also some rotational elements like shafts, where the representation is slightly different. The stiffness of the shaft is represented by a rotational spring with a stiffness kT. The rotational mass is represented by a circular element which is called the mass moment of inertia, which is called the rotational inertia, and the damping is given by a torsional damper, which is represented here. Now, let us look at the body, how we can model. Let us take an automobile. The automobile has stiffness and mass. We can identify this as one single block of mass, which represents the mass of the automobile, and the entire stiffness by a spring, and this is what we call the single degree of freedom system. We can do a little more sophistication. We can say the rear suspension as one stiffness element, the front suspension as the second stiffness element, which corresponds to mass damping element, and this has two motions, one on the rear suspension, one on the front suspension. So, this is a 2 degree of freedom model. Yeah.
Small break in the audio. I'll just take it, sir. Suddenly I'll change the battery or something maybe.
Yeah. Can you hear me now?
Yes. I'm really sorry because the break was happening. Every word.
Should I start from start?
Yes, sir.
Okay. Just 1 second.
I'm really sorry, sir.
That's okay.
I'll have to change that.
Yeah.
Start, sir?
1 second, bro.
Yeah, okay, one.
Can you hear me now?
You can start, sir?
Yeah. So, in this lecture we will talk about the use of control system on a typical engineering application, that is controlling a vibration in a beam. So, before we do that, we need to introduce vibrations. So, in this lecture I will first introduce vibration and then go on to talk about the control system that we develop for this simple control system that we developed for the vibration of a beam. So, what is vibration? So, vibration represents a motion of the system caused by the combined action of the inertial force due to the mass of the structure and the stiffness force caused due to elasticity of the structure. So, the combined action gives what is called the vibration. So, it requires a initial movement, as we see in this tuning fork. So, when I give an initial movement, it moves, the two forks moves up and down, vibrates, and this is caused by the mass and the stiffness of the structure. So, this is essentially a dynamic phenomenon where the input as well as the output is time dependent. So, how do we model the dynamic systems? So, the modeling requires certain elements. So, if it is a translational elements like a beam or a plate or any such devices, we represent the stiffness by by a spring of value k, the spring coefficient. The mass is represented by a block of mass m, represented by m, and whenever we give a disturbance, this disturbance does not continue for long, it dies after some time, and that is caused by damping force. And there are different kinds of damping, and here what we have represented is one particular type of damping called the viscous damping, which is represented by a dashpot as shown here. If it is a rotational element, as in the case of a shaft or any rotational member that for which we need to study the vibration, the rotational stiffness is represented by a helical spring of constant kT. The mass, the rotational inertia is represented by a circular element with the coefficient j, which represents the mass moment of inertia, and a damper, again a viscous damper, which is called the torsional damper. How do we model the systems? Let us take an example of an automobile. In this automobile, basically this whole thing can be represented by 1 degree of freedom or 2 degree of freedom or even many more degrees of freedom. If it is modeled as 1 degree of freedom, then the entire mass of the automobile is blocked as mass m here in green color. Then we have a stiffness k, which represents the stiffness of the automobile, and it is only movement is only parallel to the ground. So, basically, so that represents the dynamical systems in terms of springs and masses. We can do a much more sophistication. We can actually model separately the rear suspension and front suspension by respect to spring constants k and the damper element c. So, this will have two motions, one on the rear and one on the front, perpendicular to the plane of the paper, and this represents 2 degree of freedom system. We can also model the headrest, we can model the passengers, we can model everything all in terms of spring and mass, and more sophistication we can build into the system, a vibrating system. So, let us get into some basic definitions here. So, first of the definition I would like to define is degree of freedom. How do you define a degree of freedom? It is the number of independent coordinates required to describe the motion of a system is called the degree of freedom. So, thus a free particle undergoing general motion, especially if it is a free body, then it will have 6 degrees of freedom, that is 3 translation motion and 3 rotational motion. So, in aircraft terms it are called yaw, pitch and roll motions, that are the rotational, and the movement in the 3 coordinate directions is the 3 translation motion. Furthermore, if it is an elastic body, we can idealize into n number of masses. So, so basically if there are n number of masses, it becomes n degree of freedom. So, typically an elastic body can have infinite degrees of freedom. However, in most cases, especially in control system design, we do not require such sophisticated model. We can do away with only few degrees of freedom, that is, we can model the system with very few degrees of freedom and then still do a very good job in designing the control system. Next, we will define what is free vibration. The free vibration is a vibration takes place in the absence of external force. That is, we just give a disturbance, say for a cantilever beam, then the beam goes up and down repeated motion at certain interval of time, and this interval of time by which it vibrates is called the natural frequency of the system, and that is what I have defined next. And this is related to the time period, the period by which it causes the mean position up and down. And this frequency can be expressed in various form. It can be expressed in cycles per second or radians per second, or it can be expressed by hertz. Omega is equal to 2 pi f gives the relationship between the frequency in radians per second to hertz. If f is in hertz, to convert it into radians per second, you multiply by 2 pi. Next, we will talk about forced vibration. So, the forced vibration is vibration taking place due to an applied dynamic force, that is, the external force is applied. Then that force will also be applied at certain frequency, okay, which is called the excitation frequency. If the frequency of the excitation or the driving frequency coincides with the natural frequency, then a system called resonance takes place. which will basically dangerously large oscillation may result because of this. The failure of the major structures such as bridges, buildings, aeroplanes, even the MEM structures are due to the existence of resonance. So, thus the design of the control system, basically the poles is basically signifying the resonance which causes instability. At any cost the resonance should be avoided. So, now let us look at some of the simple motions. Here is a motion that is shown here, that is of the spring mass. This motion, when we plot in terms of time, if we measure the amplitude at the tip of the mass, it will look like here. It is a simple sinusoidal motion, okay. And such a motion is called the simple harmonic motion. So, it has a period t, it has a peak amplitude c, and it continuously keeps going. So, this is called the simple harmonic motion. Most vibratory system is characterized by the synthesis of many such simple harmonic motions. So, let us look at it. So, if x is a simple harmonic motion, which is displacement, where we can express either in terms of f, the frequency in hertz, or in terms of radians per second, omega is 2 pi f, we can get the velocity of that motion by differentiating this displacement x by dx by dt, which is given by here, okay, and x double dot is given by here. We also have a parameter phi, which is a phase between the displacement and velocity. You could see that displacement, the velocity lags displacement by almost 180 degrees, acceleration lags displacement by almost the velocity lags displacement by 90 degrees and acceleration by 180 degrees. So, the peak velocity is omega c and acceleration is omega square c. So, basically displacement in terms of magnitude is the lowest and acceleration is highest. We can pictorially look at it here. So, we see that displacement is many orders smaller compared to the acceleration if you plot for a typical motion. Let us come back to a single degree of freedom system where we do not have any damping here. So, this system basically can be represented by mass, spring and a damper. So, we begin the mathematical analysis by isolating this mass and drawing up all the forces and applying the second Newton's law. So, when we isolate this mass and draw the forces, the damping force is always proportional to the velocity of the system in which vibrating, that is Cx dot, and mx double dot is basically the acceleration. So, when we draw this free body and assume that whenever before vibrating, when we isolate the free body, mg cancels with k delta because of the static equilibrium, we get the governing differential equation by using the free body as mx double dot plus Cx dot plus Kx equal to 0. So, it is a second order differential equation. If you look at it, it is a second order differential equation. It is linear equation, it is homogeneous equation and it is of constant coefficients. So, basically it will have exponentials as solutions. So, C equal to St. Our objective is to find the two roots of the equation basically and find out the responses. So, the characteristic equation can be got by substituting x of t equal to C e to the power of St here into this equation and getting the velocity and acceleration and substituting it, we get the characteristic equation. This solution will give us two roots and that forms the solution here. So, the roots of the equation is given by this equation because it is a quadratic which can be easily solved. The characteristics of the roots depends upon the term inside the radical. It can be real, it can be imaginary, it can be complex. The value of the nature of the roots depends upon the value under this root. So, basically if c square is greater than 4 m k, then we have all the roots are real. If c square is less than 4 m k, it is imaginary, and if c square is equal to 4 m k, then it is what we call it is a critical situation. Once we get this S1 and S2, the total solution can be got here. And C1 to C2 are basic constant which are determined from the initial condition whether it is at rest when x at t equal to 0 and x dot at t equal to 0, that is velocity. Now, let us spend some time into this equation which determines the root. Let us consider a critical situation when c square is equal to 4 m k which will give me on solving the value for C. This is the maximum damping that a system can have, and that depends upon the characteristics of the system, namely the system its stiffness and mass, and this is called this critical damping. So, we would always like to see how much of the damping is a factor of critical damping, that is C by Cc, which is what we call the damping ratio. So, that is what we introduce here. So, once we do this, we can say the natural frequency of the system, as I said before, depends upon both the stiffness and mass, which is equal to root of k by m, and we can write the roots in terms of the natural frequency and damping ratio as given here. So, here we can clearly see if xi square is greater than 1, then this will be real, and if xi square is less than 1, it is imaginary. So, let us consider the first case where xi square is less than 1. So, then these roots of this equation can be written in terms of the complex number. We can write this root under the radical here. So, that means the roots will be of the form a plus ib. So, that is, it has both the real and imaginary part, and we define a new variable called the damped natural frequency, which is a function of the damping ratio. This damping ratio is a fraction of the total critical damping ratio, C by Cc. Once we do this, we can write the term under this radical is omega d. So, we can write my roots as psi times omega n plus or minus j times omega d, where j is the complex number. So, once we do this, we can write this equation of this form, and we can actually express this complex exponential in terms of sines and cosines, which gives me this equation e to the power of minus xi omega n t into a cos omega dt plus b sin omega dt, where a and b are arbitrary constants, can be found from the initial condition. So, this is a completely oscillatory, if you look at the term inside, this is an oscillatory function, but it is multiplied by an exponential. So, it decays. So, basically this damping effect is clearly seen here. So, this is how it is. So, it starts very high, and as the time progresses, it damps out to actually to a very 0 value. So, basically the vibration vanishes, and that is mainly because we have included the property of damping here. Now, let us take a case where it is critically damped, that is the radical is 0. Then we have two repeated roots S1 and S2. For repeated roots, the equation the solution becomes here. So, you clearly see that as t increases, the response increases exponentially with time, I mean linearly with time, multiplied with this constant here. So, again here C1 and C2 are determined from the initial condition. So, if you plot this response as opposed to the oscillatory response, you clearly see after the initial surge of response, it comes to 0 practically very fast. Okay. So, this is a totally different behavior when the radical is changed for this kind of solution. Next, let us take a third case when psi, the damping ratio, is more than 1. When it is 1, the roots can be written as xi square minus 1. So, it has two roots, then it has S1 and S2 are real. That means basically it has no oscillatory component, and the system comes to rest very fast. It is completely over damped system. So, we have under damped, critically damped and over damped system, and this plot basically gives you the overlapping response of these three cases, and you see that the critically damped and the over damped are not of much interest to us because it does not vibrate, it comes to rest very fast. What is of importance to us in the control system is the under damped case, where we still get an oscillatory motion, and we should make sure that this oscillatory motion does not increase in time, as the time progresses. So, let us look at now how do we construct the stiffness elements for the case of the simple structures. For example, if we have a rod, if we have a rod here, if the rod is basically, say if it is fixed here, let us put a fixity here, then we have the displacement will be, my delta displacement will be PL over AE. Okay. Now, basically my stiffness is defined as force by deflection, which is nothing but AE over L, and that is how we get here, because this is a predominantly large displacement. All displacements are at the tip here at this position. Similarly, in the case of a beam, say cantilever which is fixed at one end and a load is applied in the transverse direction, the maximum deflection delta is in the transverse direction delta, and using the strength of materials approach we can easily find that the deflection delta will be equal to FL cube by 3 EI. So, that means basically F by delta is the force by displacement 3 EI by L. So, that is what the stiffness is here 3 EI by L. So, wherever we are trying to find out for the element, the boundary conditions plays a big part. We will see in the next case how the boundary condition plays a big part in the for example, if it is a simply supported beam or a fixed beam. In the case of a fixed beam, we see that the maximum deflection is given by FL cube here, FL cube by 92 EI. So, F by delta is 92 EI by L cube, which is totally different from what we had for a cantilever beam. If it is a simply supported beam, maximum deflection from the strength of materials approach is FL cube by 48 EI, where so the stiffness for the simply supported case will be 48 EI by L cube. So, basically the boundary condition of the structure determines the equivalent stiffness that you are trying to calculate, which is very important, especially if you want to construct a vibratory system from the actual system in terms of springs and masses. In the case of a torsion, very similar to that of a beam of a rod, if it is fixed here, the total moment will be kT into theta. So, basically this kT will be Gj by L instead of Ae by L in the case of a rod, where J will be a function of the diameter of the shaft. So, similarly you can find out the equivalent stiffness for many systems in order to construct the spring mass damper, because which is essential for us to do the control design. Mass element, as I said, is represented as mass m for translational motion, and J a rotational element for the rotational inertia component, and the energy associated. So, whenever you have a mass, there will be a kinetic energy associated, which is half times mass times velocity. If x is the translation motion, x dot is the velocity, half mx square. If in the case of rotational motion, J is the mass moment of inertia. If theta is the motion and theta dot is the rotational velocity, then the rotational energy will be half J into theta dot square. Let us come back to the single degree of freedom forced vibration now, because that is where it is very critical, because there will be forcing in many of our system what we are trying to design. So, this is basically is the same spring mass system, where you have spring, damper, single degree of freedom system. There is only one motion x, but in addition to this there is an additional force F of t, which is a dynamic force that is act on the structure. Again we isolate this the free body. So, when we write the free body and use the Newton's second law, then we get the differential equation of motion. An additional term F of t comes into the right hand side, that is mx double dot plus cx dot plus kx equal to F of t. So, here the solution of this is again second order. So, in the previous case we had 0, here we have this force, which I have assumed it as a cosine variation. F of t can be f naught into cosine omega t, it can be anything, but here we have taken it as cosine omega t, where this omega is the driving frequency. So, this solution of this has two components. One is the complementary solution, which is essentially the free vibration solution, we call it as a transient solution, and the particular solution which we call this steady state solution. And we assume that it is under damped system, because that is of interest to us when xi is equal to less than 1. So, the steady state solution we have already found out from the free vibration, which is given by here e power minus xi omega n t into a cosine omega dt plus b sin omega dt, which we already know. Now, let us see how we can determine the steady state solution. So, if you look at this, if you look at this relation, we have f equal to f naught cosine omega t, we assume that the displacement also follows the cosine part, but with a phase angle phi. So, from which we calculate, we assume the solution of this form, where x is the steady state solution amplitude, x dot is the steady state velocity and x double dot is the steady state acceleration. We substitute it into the equation, and then we get two equations in terms of, we group the cosine omega t terms and sine omega t terms from here and expand this using the cosine trigonometric identity. We get this following two equations, which is given by equation 1 and 2. Now, we solve this two equation to get the value of x, which is given by this equation. So, f is equal to f naught into this k minus m omega square whole square plus c omega whole square, and this is the phase equation. So, the two unknowns are x and phi. So, we get these two equations to solve this. So, the total solution will be the transient solution and the steady state solution. One thing that you can see here, if c is equal to 0, okay, and we see that when omega n, that is natural frequency, is root of k by m. So, omega n square is k by m. When I take this here, when c is 0, when omega becomes root of k by m, then there is the x goes to infinite response. That is, the resonant condition gives excessively high amplitude, which has to be avoided at any cost. So, here is the response. The red line says the steady state response, the blue line says the transient response, which dies down after some time, but the steady state does not die down, it keeps on going. The total response is the sum of these two response, which is given here. Okay. So, here we take this we take this equation here, and we form what is called x k by f naught. We actually take this f naught down and multiply by k and simplify the right hand side, and we get what is called a magnification factor. And this magnification factor tells how much of the response is amplified because of the presence of the dynamic amplitude. So, here we can see the plot here, which essentially shows the magnification factor as a function of the frequency ratio omega by omega n. We see that when omega is equal to omega n, for small damping there is a steep increase in response, extreme response, which has to be avoided at any cost. Now, let us come to the basic control concept. How do we use this vibration knowledge to design the control system? So, here we see that a typical structure, smart structure, contains a structure, a smart actuator, a smart sensor, a controller, and a disturbance. So, basically what happens, the sensor senses it, and together with the actuator input forms the error signal, which is sent to the controller. Okay. There is already an applied force. So, when this is applied counteractively to reduce the vibration of the structure. So, to typically show, here is the beam that is shown here, and this is the patch, which is the sensor patch, and this is an actuator. So, the actuator is smart actuator. It can be based on PZT or magnetostrictive or Teflon. In this demonstration, we will actually show you how we can construct a smart structure using PZT actuators. So, first of all, the first thing what we have to do for this demonstration of this vibration control is how do we build the smart structure. So, what we do is we are going to demonstrate it on a beam. So, we are going to take a beam, cut to the desired length. It can be a metallic beam, it can be a composite beam, it can be any other beam. Then we clean the area where we need to attach this smart patch by using an ethyl alcohol, so that any impurities that are there is removed. Then we use epoxy for the insulating area. That is, so we do a coating of the epoxy and we make it, let it cure here. Then what we do is, in order to build the lead wires at the later part, we attach a copper tape on the back side of the beam, where if you are attaching the patch on the front side, we are putting this copper tape at the back, and we use epoxy to attach the piezoelectric actuators into the into this region by keeping the edges down, and we remove the excess tape and we solder the wires in order to connect to the control system. So, in order to demonstrate this pictorially, we show this here. So, this is a beam that we have used it, the cut to the approximate length or desired length. Then we have isolated the region where we need to attach this piezoelectric patch. So, we have coated with epoxy in this region, so that the impurities are removed. Then we attach the negative the copper tape on the back side of where we need to attach the patches, so that it making more conductive. Then we actually fix the patch using epoxy, form it down, remove the excessive tape around this, and finally the patch is fixed here and we solder the tape. So, this out. So, whatever I have explained here, we are putting it in the actual structure here. So, now what is the objective here? So, objective here is, we have a cantilever beam which is applied to some dynamic force, and our objective is reduce the vibration of this due to the presence of the smart patch. So, how does the smart system, the control is designed basically in order to make sure that this smart patch imparts necessary counter force to balance this vibration. So, before doing that, in our control design we also talked about open loop control, where no error signals is there. So, how basically the smart system can be used open loop control without any error signal. So, here we have a bimorph beam. Bimorph beam is a beam which contains the piezo patches or the smart patch both at the top and the bottom surface. So, here is a bimorph PVDF film. So, what does this do? Basically, when we energize this beam, basically it creates two forces on the two opposite direction at the tip as shown here, which eventually causes a moment. Okay. This moment will cause the beam to bend. Okay. So, basically if there is a vertical force acting in addition to the effects of this PVDF film we have. So, basically this will counteract the beam bending. Okay. So, the effective structure what we are trying to solve is a cantilever beam with a moment as given here. The moment is given by 2 sigma v by t, that is basically due to the voltage that is passed on to the piezoelectric patch here. So, we actually derived this in our earlier classes, that the tip displacement due to the mechanical load P and the voltage given to the smart patch is given by this expression here. So, basically you see that for a given P, the P is fixed here. If the voltage is increased, this net value keeps on decreasing, and it will come to a value such a way that when we can basically make the displacement due to applied load 0 by increasing V enormously large. So, this basically no error signal is there, it is just open loop. So, basically we are trying to apply a voltage which to counteract the deformation that is caused by the mechanical load. So, if you here there is a plot which basically says the value of the displacement as a function of voltage. So, when the voltage is 50 volts, this is very large, and this becomes smaller and smaller as we increase the voltage, and eventually we can make the total displacement 0. So, that is the smart concepts. Now, here we do not know. So, this voltage V is random, we do not know how much to apply in order to get it to the required level. This is avoided by the closed loop control, which we described in the control lecture. So, the closed loop control along with the error signal can help to reduce this vibration levels to the desired levels. So, let us see how we can design the closed loop control system. So, now the active control strategy, what are the different? There are different control strategy, there are different kinds of disturbances, and there are different physical objective of the control. So, if you look at it, the control can be semi active or fully active. Semi active is we basically change the stiffness and the damping of the system by some means which are not active. In the fully active system, where we actually design a feedback or a feed forward control using the error signals. So, these are the different strategies that one can apply. If you look at the disturbance, there are two different disturbance. One is a completely random, which is normally in practical cases. One is deterministic, we give a predetermined input. So, that also depends on the type of control system that we need to design. And last but not the least, the physical objectives. There can be a global objective that whole plant we need to reduce the vibration, or we have to do only a local control. So, that depending upon the objective, we need to define the control system. Let us talk about each one of these a little bit more detail. The active vibration control, what we are talking about, can be passive. That is, basically in the passive, we basically increase the damping material. So, basically we put a new material which can give an extensive higher damping in order to control it. So, there is no active no change in the stiffness or anything is done. So, in the semi active or adaptive passive, we change dynamically the stiffness and the damping of the system by some means by actually using constrained layer damping or some other means where we can actually do. And a fully active is like using a smart layer, where we basically energize the structure with different voltage levels, which dynamically changes the voltage levels in order to make sure that the vibration levels is comes to the minimum level what is desired by the designers. So, the passive is basically mass, stiffness, damping, quantity and distribution fixed at the design stage. So, we have an enormous amount of damping. In the semi active or adaptive passive, stiffness and damping properties are changed to adjust the internal dynamic force to minimize the response, and in the fully active says dynamic forces are applied to the system to minimize the response, that is automatically. So, let us do the analysis of a beam in this case. So, the beam equation and transfer function. Here beam is modeled again as a single degree of freedom. It is a very simple control strategy to demonstrate how control system can be designed. Here we are designing a feedback control to reduce the vibration. Okay. Now the sensors can be, we could have used displacement, we could have used velocity, we could have used acceleration, but what we have used here is basically the acceleration. Acceleration is basically used to construct the error signal. The error signal is very key component for the feedback control. So, we use the measured acceleration at some point, typically the tip as the basic input that goes into construction of the error signal, which is fed to the controller through the to the actuators. So, the transfer function if we did not have an error signal, it would be 1 by this denominator. Since the error signal is given here, the transfer function is modified, because acceleration is proportional to m omega n square. So, the omega n square term is coming here. So, this is basically the controls is the transfer function that requires. So, this can we can determine the poles, there is no zeros here, and we have to see how we can design the control system here. So, first we do an experimental study. So, in the above equation, the natural frequency omega and damping is to be known. So, we measured it experimentally. How do we measure it? We can take the time response. This is a typical time response that is given here. Okay. So, this goes up and down here. So, we take the period, find the period, and from the period 1 by period multiplied by 2 pi will give me the time response, which is in our experiment was found to be 44.9 radians per second, or it can be expressed also as cycles per second. We found that t to be the period between two successive peaks to be 0.14 second. Then how do we measure the damping? The damping is measured by what is called the logarithmic decrement, which is normally represented as delta. See, delta will be equal to 2 pi xi by root of 1 minus xi square. Okay. So, now what we do is the ratio of two successive amplitudes. So, there is a decrease. Okay. This is taken. Okay. So, delta is nothing but the log of n by n plus 1, that is the ratio of two successive amplitudes, So, we measure the two successive amplitudes. So, then we use this equation here to actually find out the logarithmic decrement, and once we find that, we find the value of xi, and when we did this we got this value to be 0.0168. So, we designed this controller, a simple PID controller, using the MATLAB Simulink. So, MATLAB has a very good toolbox called Simulink, which is exclusively dedicated to design the control algorithm, and there is a DSpace software, which is a data acquisition software, which can be linked to MATLAB Simulink to enforce the control. So, basically we have a piezo patch is put on a beam, which is act as a sensor, acceleration is a sensor, which is passed to a low pass filter, then analog to digital controller to enforce the feedback control. So, this constructs the error signal, which is given here and which is amplified. The power has to be amplified due to restrictions in the voltage what we have, and then the control is enforced. So, this is a simple flow diagram that shows the control strategy that is employed to just control the vibration of a cantilever beam using piezo patches. So, let us go by step how we did this. So, first what we did here is, first we have to place the sensors and actuators. We have shown you how to fabricate how to put paste the sensors in the starting of this lecture, how to put the sensors here, and once the sensor is placed here and the actuator inputs, actuator is needed to input the external voltage that is required for control. This sensor near the tip measures the acceleration, and this is used along with the actuator input to construct the error signal, which is fundamental to feedback. Okay. The actuator inputs the external voltage, which helps in developing the control force, because that is what we need, and also the error signal. Then the accelerometer measured has to be pre-amplified. So, it is sent to a signal conditioner. A signal conditioner is shown here. We provide the power to the accelerometer, which helps to pre-amplify the signal. Because that is required in order to get reasonable responses. Then the output from this conditioner is sent to a low pass filter. Why do we need this? Because basically when we measure the responses, experimentally measured responses is polluted with noise. So, in order to get a cleaner response and which are easier to read and more accurate results can be predicted using the by passing it through a low pass filter. It also helps to identify the cutoff frequency because it gives us the frequency sweep. So, it helps us to identify the cutoff frequency, whether we are working in the correct frequency regime for which the control is to be enforced. Next we send it to analog to digital converter, and the output is measured. So, that is with noise filtered out, the sample is sent to the D space, again the D space controller, which runs through the gain. So, the gain is another. So, how do we choose the gain? So, there is a parameter in D space where we can change the gain to be inputted to that, because the gain is a relationship between output and input, which is an important parameter. So, it runs through a gain. So, first it runs through a unit gain, and then the gain is constantly increased or decreased in order to see at what point we get the control. The whatever that is going into this ADC is now viewed in the oscilloscope for the output. The input voltage is first seen. In traditional systems we cannot exceed more than 10 volts, because for operating conditions more than 10 volts is more dangerous. In many cases, like in real structures like aircraft, large voltages are not available. We have to work with small voltage and then use some kind of amplifier to amplify the voltage. So, we put the threshold of the voltage to be 10 volts in many cases. So, here we have put the threshold to 10 volts, and we make sure that the input voltage is not exceeded, input voltage of the response that is coming out is not exceeded. Next we run through the feedback gain. So, the sensor output is multiplied by gain, okay, and it loops over over and over again, and see whether the vibration that is initially there due to the applied force is beginning to decay. Okay. So, and once this comes here, we look at the output also at the oscilloscope. When we do that, we also make sure that the voltage of the output voltage is also not exceeding to 10 volts, because that is a threshold that we have put here. So, the low pass filter now, after the output is there, is again passed to a low pass filter or a power amplifier, because the output may be very small because the voltage levels are very small. So, we require a larger voltage because this voltage has to be amplified in order to give the necessary control force for the decay of vibrations. So, that has to be done basically to make sure that the output is sent through a power amplifier, which is shown here. Okay. So, this power amplifier amplifies voltage for low pass. Since D space voltage cannot exceed 10 volts threshold, the signal must be amplified to increase the voltage to piezoelectric volts. So, in this case we need to calibrate the power amplifier, and we have done this for about 15 volts. So, finally, after passing through, after preliminarily cleaning up all the signal, we send the voltage is applied to the piezoelectric actuator, which is shown here. The piezoelectric actuator will bend or contract to apply the control force on the beam. Then we can clearly see there is a reduction in the vibration levels that the beam is vibrating due to the applied force. So, let us look at some of the results here. So, what we have found here is, when the beam was tested with various gains, the positive feedback gains made the beam unstable. So, the positive feedback, in fact, because the omega n square is there, is trying to put the poles onto the right hand side, right hand side of the S plane, which we said that is very bad for the stability of the control system. So, basically the positive gains is not helping in control. However, when we decrease the control and we give the negative, so when we make that negative feedback, basically that is helping to put the poles onto the left hand side of the S plane, basically to ensuring the control. And in the left hand side, higher the gains, more was the control that was we could see. Of course, we have put it in a particular positions which was optimized to see that at that position, when we feed the error signal from there onto the actuator, we know that we can get maximum control. But it also depends upon where you pick the error signal and where you actually feed it to the controller, to the actuator. So, here in this case the location was such a way that higher the gains, more effective was in the reduction of the vibrations. So, this is basically gives the response without vibration. So, you see that there is a peak vibration here starting and starts to decay after some time, where the damping was basically 0.0168, that is the critical damping, that is the ratio of the actual damping to the critical damping. And then after the 3 feedback loops with 15 volt amplification, we have to amplify the voltage whatever that is coming here to 15 volt. We see that there is a significant reduction in the vibration levels, which is shown here, okay. And the damping was reduced, was increased from 0.01 to 0.05. So, there is a significant increase in the damping, which is making the response to come down. So, basically the closed loop feedback was effective in increasing the damping levels, and that is the objective of the control anyway, and we did a closed loop feedback system here. So, here is a plot which is superimposed with the results with no controller and with a feedback PID controller. So, we see that there is a substantial reduction in the responses as the time progresses, even though initially the controls were small at the initial times, at very small times, but as the time increases there is a substantial reduction. So, sine wave decays considerably faster. With grain applied to the beam, we see that the vibration is more or less controlled. So, in summary, what have we learnt in this lecture? So, basically in this lecture we helped we understood the concept of vibrations. How do we model the vibrations in terms of springs and masses, why damping is very important, how the damping reduces the vibration, what is free vibration, what is forced vibration, how do we control the forced vibration, what are the equations there, what is magnification factors, why is resonance very important, how is resonance related to poles. Basically, if it is on the right hand side, it causes right hand side of the S plane, it causes extreme buildup of the responses, which we need to avoid, and causes unstable control system. We also talked about what is a smart structure, what are the basic ingredients of making a smart structure, that is how do we construct a smart beam basically from first principles, how do we do that, how do we use this vibration experience to actually build the system, the smart system, especially how do we bond the piezoelectric actuator to the structure, what are the things that you need, and what are the essential steps that you need to undertake to build the control systems, that is the low pass filter, the analog to digital converter, how do we construct the feedback system, how does the actuator signal goes to the sensor, etc. So, this is a very rudimentary signal, and this can be extended to many bigger system. And we found that we also demonstrated the use of this on a simple cantilever beam, and we showed the results. In the results, we have said that how do we experimentally characterize the damping using logarithmic decrement, how do you measure the natural frequencies of the system, also was discussed here. And finally, the results, we found that the feedback or the error signal considerably changes the pole locations. So, basically when we have a positive feedback gain, we said that it was putting the poles onto the right hand side of the S plane, which is completely undesirable for us from the control point of view. So, basically we just gave a negative feedback, that is the gains were negative, and this basically shifted the poles from the right hand side to the left hand side, and we started getting control. So, we showed that there is a significant reduction in the vibration levels by having a negative control, and for which we also said that one of the important aspect is the output voltage has to be available in most control system is small, we have to put a threshold, and because of that we have to pre-amplify the output voltage so that the power amplifier is calibrated for that, and using a 15 volt calibration we found that there is a substantial reduction in the vibration levels. So, with this basically we have understood how a simple controller can be designed using the knowledge of the vibration. Thank you.